Okay, folks, we can get started. How is the installation of the build environment going for people? Any gotchas or anything? I see some thumbs up. Okay. I think, as I mentioned last time, we encountered one small gotcha on some Windows machines. It's a really easy fix. You just may need to install a driver. So I think Parker posted some instructions on that, and then Giacomo backed up those instructions with a little demo video that demonstrates how to fix that. So should you encounter that bug, there should be some resources there to help you overcome it. Any other questions from anyone about anything else? I'll just remind you that we start lab today. So for the Monday folks, I'll see you in the lab this afternoon. I'll remind you also that anyone is welcome to attend any lab section. You are required to attend the lab section in which you're enrolled, and I ask that your lab partners also be in the same lab section in which you are enrolled, but you're welcome to come to any of the lab sections. And so long as there's a seat available, you're welcome to join us and to, work ahead a little bit. I wanted to say just a couple things about this week's checkoff. This week's checkoff is different than all of your subsequent lab checkoffs in a couple of ways. One is you will find that this week's is quite light. I don't expect that anyone will have any trouble whatsoever getting through this week's checkoff. And furthermore, to a much greater extent than all of your subsequent checkoffs, this week's is rather procedural. There's a set of instructions to follow that describe how you're supposed to put together a circuit and get a demo to run. In all of the future lab checkoffs, there won't be a procedure to follow, there will be an objective to meet, and it'll be your job to design some solution that meets that objective. And so I'm telling you that just so that you don't get a false impression this week of what the rest of the lab sections are going to be like. I'll mention just by the way that the reason this week's lab section is a little bit different and a little bit lighter is because experience shows that for the first week and a half, 2 weeks of the semester, there's a lot of fluctuation in enrollment. People are adding and dropping, and there's a lot of sort of chaos. And I like for things to have stabilized a little bit before we really start getting into the meat of things. The other reason that it's a little bit lighter this week is I will do my best throughout this whole semester to cover in lecture all the material of relevance for that week's checkoff. Because we're just getting booted up on this whole system, there's a lot to cover. And so an extra week for me to cover some stuff is helpful. Okay. But that said, you are extremely welcome to work ahead. And I think it would be a really good idea to do so. So any questions about any lab expectations or anything like that before I get into content? Okay, that being the case, then what I'd like to do is I had just a little bit of wrapping up to do with regard to last lecture. I'll remind you that what we were doing last lecture, we spent the first part of the lecture providing sort of a high-level abstract overview of the hardware that's available in the RP2040 microcontroller and the software infrastructure that we'll use in this class for configuring and controlling that hardware. And then so we talked about that largely in the abstract, and then we reinforced the stuff that we had talked about by looking at an actual example and showing this infrastructure that we're using to control some actual hardware. And the example that we looked at is the same example that, anytime you're learning a new microcontroller, it's the first example you always look at. It's blinking an LED. And what we did last time is we went through this code and we got to a particular line. GPIO put is, I think, the one that we investigated. And we demonstrated how when you encounter a line of a program in this class that you are unfamiliar with or that you would like to learn more about, we demonstrated the mechanism by which you learn more about what that program's doing. So in particular, what we did here is the first place that we went to learn about that particular CSDK function GPIO put was the hardware API guide, right? So we went and we Googled RP2040 hardware API. There's also a PDF version of this linked up on the course page. But we went here, and you find the section associated with GPIO, and there's going to be a whole bunch of functions listed here. Among them will be GPIO put and all the other ones. It's in there somewhere. I'm not going to go through and find it at the moment. GPIO get, blah, blah, blah. Anyway, it's in there. So you would go and find it in here and click it, and it would tell you a little bit about that. There it is. It tells you about the arguments of that function and what it does and so forth. The other thing that we could do and that we demonstrated is any function that you're unfamiliar with, you can go in and look at its declaration and implementation. And so what we did last lecture is we started going down and looking at the implementation of the CSDK functions, demonstrating that as you go deeper and deeper into this SDK, we're crawling down towards the registers, right? And so what we did is we said, oh, when we call GPIO put, if we're setting that GPIO high, it calls set mask, and we went and looked at that. And then we noticed, oh, when we call set mask, all that it's doing is changing the field, the GPIO set field of this SIO hardware struct. And we went and looked at that field, and we said, ah, it's just that register, SIO GPIO out set offset, which if we went to, now we're at the very bottom of the SDK, we could go look at this, and we find an actual memory address associated with that register. And what we showed is we could then go to the RP2040 datasheet, and we could go to go on, RP2040 datasheet. We could go to the appropriate chapter. In this case, it's the SIO chapter. And we could look down at our registers and look at the appropriate offset address. It was hex 14. And learn more about that particular register that that particular C function is touching. And what we noticed is this particular one, when we write to it, it does an atomic bit set of the GPIO out register. So it sets the GPIO outputs. And I wanted to do just a little bit of wrapping up on this story by demonstrating a couple more tools for investigating this code using some infrastructure that's new to this class this semester. I'm going to try to demo this live, which is always risky. But another way that you can investigate this program is by way of our debugger, which you all receive in the lab, and I'll show you how to set up. And if we wanted to, we could run the debugger on this program. And for those of you that have done this kind of thing before, this is exactly the kind of debugging interface that one would expect. For those of you that have less experience with these debuggers for embedded systems, I'll just tell you that what this tool is it is a mechanism by which you can load your program onto the microcontroller and ask for that program to pause at certain points and essentially tell you all the state of the system. So for instance, we could say, I would like for this program to run until it hits this point and this point, at which point I'd like for you to pause. So it pauses there, pauses there, pauses there again. And when it pauses, we can look at a whole bunch of state associated with the system. So over here, we have the call stack. This is showing us all of the functions, which called functions, which called functions. It shows us sort of the state of execution of the system. And I wanted to show you one other interesting tool in this particular debugger of relevance to the conversation that we were just having, which is this, trying to make a little room here, this peripherals window down here, which shows us the value of every register in the system. And so we could go to the SIO section here. We could look in particular at the GPIO out register, and we would notice that it is set to hex 02, bunch of zeros. And if you, this is in hexadecimal, right? So each one of those digits represents 4 bits. If you were to count up there, what you would notice is bit 25 is set to 1. The position of that 2 means bit 25 is set to 1. Bit 25 is associated with GPIO 25, which is the one that the LED is attached to. So the LED is on. If we run this to the next breakpoint, we will notice that we've turned the GPIO off, and so the GPIO out register is now all zeros. So I'm just demonstrating that this is yet another mechanism by which you can investigate the state of your registers and the state of the system. It's a really, really useful tool. By the way, the observant among you may have noticed that I slightly changed this program since last time. Last time we had sleep milliseconds there, and this time I have busy wait milliseconds there. The reason for that is the sleep SDK function, under the hood, it actually puts the RP2040 into a low power mode. So it turns off a bunch of systems, as many as it can, which can cause the debugger to hang. There's a solution to this. We can add a few lines of code to prevent the debugger from doing that. For our purposes, the easy solution is just sleep becomes busy wait. Phenomenologically, it's the same. It's just a pause, but this does so it doesn't shut anything down. It just spins there for a while. So it interacts more nicely with the debugger. Any questions about this stuff? The only other piece of this demo that I wanted to show you is, you may have noticed that in this project, there were actually two files that you can modify. One is our source file, blinky.c, and then there's this CMake lists.txt. Every project that you download will include this CMake lists.txt file. CMake, incidentally, is it's an infrastructure that allows for you to essentially tell the compiler how you would like for the project to compile. It's a little bit clunky and takes a little bit of getting used to, but as you get used to it, I think you'll find that it's actually a really useful tool. All that I wanted to mention about this is when you import one of these programs into this VS Code environment, most of the stuff in this CMake lists gets automatically populated. The stuff that you will likely have to pay attention to is everything from here down for any one of these projects. And I wanted to just talk through this a little bit. So in every one of these projects that you download, there will be a line in your CMake list called add executable. That is essentially us just telling the compiler what to call this project we're about to compile. When you produce executable files, what should you name them? We're saying, please name it Blinky. The next line here is target sources. The first argument of this is the name of that executable. The subsequent arguments are the name of every source file, every .c file associated with this project. For Blinky, we only have one, but in the event that we were pulling in some other libraries to do some other stuff, like for instance in lab 2, you'll pull in a VGA library that includes a .h file and a .c file. The .c file, the source file associated with that VGA library, would be included in this list. If you forget it, the compiler will throw an error. It's a pretty clear error, right? But it's an easy thing to forget, so I'm just pointing that out. The private there, incidentally, is just in the event that we had a big directory that included a bunch of projects. Private means the following target sources are only for this project in this larger directory. Link libraries. This is another important one for you to be aware of. This is where we link all of the C SDK libraries that we will be using. So you will notice in this particular project, we have the executable name, and then the only library that we're linking is pico_standard_lib. The reason we're linking that is because in the source file, we are including that. If we had other SDK files that we were pulling in there, hardware support libraries and so forth, we would add that to this CMake lists. And in the next demo that we look at, we'll see an example of this. This too, if you forget to do that, you'll all forget to do this because it's the easiest thing in the world to forget. The error that the compiler, actually it won't throw an error, it'll throw you a warning where it'll look at the C SDK function that you're attempting to lose and tell you it's doing an implicit definition of that function. What that's telling you is, I don't know what this function means. And that should make a little alarm bell go off and go, oh, I forgot to modify the CMake list file. Okay. And then the Pico add extra outputs here. This line is necessary if you want for the compiler to generate executable files that are compatible with flashing the board over the USB connection, which is kind of handy. Okay. Any questions here? That sort of concludes my conversation of Blinky. And unless there are any more questions, I want to start talking about some other peripherals and so forth. Okay, so then let me give you just a little bit of context here. So as I mentioned, I think on the first day of lecture, in every lab, for every lab assignment in this class, you are given a starting point, some demo code from which you will start, and then you'll modify that demo code in order to meet the objectives of the lab. What I would like to do this lecture, probably this week and maybe Monday, is incrementally build up to the demo code from which you will start lab 1. Now, one approach that we could take here is I could pull up the demo code from lab 1 and we could just start talking through it. That seems a little bit mean. Given that all of this is so new, I would like to start with the simplest examples conceivable and then incrementally build up complexity. We'll add one peripheral at a time or one algorithm at a time until we arrive at the demo code by Monday. So the particular stuff that we have to get over that's of relevance for lab 1 is SPI communication. So communication with external peripherals over an SPI channel. I'd like to talk about that. I want to talk about the timer peripheral that you'll be using in Lab 1. And I want to talk about how we associate an interrupt service routine with a timer peripheral for repeated execution of code. That's how you're going to do audio synthesis. I want to talk about our audio synthesis algorithm that we'll be using. Direct digital synthesis is the name of it. So that's going to be a topic of conversation. And there was one other thing I wanted to discuss of relevance, proto-threads, which is the threading environment that you all use to organize your program. So I'm not going to cover all of that today. What I would like to do is start with a simplified example that allows for us to talk only about SPI communication, timers, and timer interrupts. And then we'll add some complexity on. So let me then pull up a new demo, new project from example. And the particular demo that I want to pull up, come along. If this is too slow, we can just look at it. Oh, there we go. Let me see here. My goodness, this is slow. Audio, timer, interrupt, DDS. Put it in downloads, that's fine. Okay. I would like to look at this demo. And the way that I would like to talk through this is, first of all, let me tell you what this program is doing. All that this program is doing, if you build the associated hardware and run it, what it does is produces a pure tone out of a speaker. And so you load this onto the Pico, you set up an SPI DAC connected to the Pico, plug in a speaker, and what you'll hear is beep just coming out the whole time. The way that it does this is it sets up a timer interrupt to perform this direct digital synthesis algorithm and generate a pure tone. What I would like to do is go through this program, well, probably 2 times. The first time we go through this, I'd like to just look at the structure of it. Here's an interrupt service routine. Here's where we set up the interrupt service routine. Here's where we're setting up an SPI channel. And the algorithm that's being implemented, the first time we go through this, I'm going to kind of wave my hands at and say, we're just declaring some variables here. We're doing some math on those variables here. And then next lecture, we'll come back to this and we'll go through it a second time and look at the actual algorithm that's being implemented. So the first time through here, we're just going to look at the structure. Here's a variable, right? And then the next time through, we'll describe what that variable actually represents and how it's being used. So this time through, all I'd like to look at is the structure of this program. And what you'll see at the top is a bunch of includes, and we're including here some standard C libraries, standard IO and math.h. And then we're including a series of libraries from the C SDK. Just like last time, just like Blinky, we're including Pico standard lib. And then we're including 3 of these low-level hardware support libraries. One for the timer peripheral, one for interrupts, and one for SPI. Now, as I just mentioned, every time you pull in a new one of these SDK libraries, we better add it to the CMake lists file, right? So if we open up CMake lists, we should expect to see in the linked libraries Pico standard lib, hardware SPI, hardware timer, hardware interrupt. So we pull in a few libraries, and then at the top of this program, we just declare a few variables. And like I said, I'm going to talk next time about what these variables are actually doing. For now, we're just going to say we're declaring some stuff. The first things we do is we create some macros, pound define alarm number 0, pound define alarm interrupt, timer interrupt 0. I will remind you that each one of these macro declarations is not a variable. There is no place in memory set aside for something called alarm number. This is a textual replacement. This is a matter of convenience for us as the programmer. So now, everywhere in our program that the text string alarm num appears, 0 will be replaced at compile time. So okay, we're giving ourselves some shorthands for a few things. A shorthand for 2 to the 32, a shorthand called FS for 50,000. And then we're declaring a few variables. A few unsigned ints, one unsigned int called phase accum main, another unsigned int called phase increment main. Like I just talked about, we're going to talk about how these are used next time. But for now, it's a couple of unsigned ints. Volatile unsigned ints. anybody know what volatile means? What we're telling the compiler when we say volatile? Aiden?
You have to get the value every single time you get stored in a register.
That's right. So Aiden's answer, which is correct, is what this tells the compiler is every time you use this variable, please go retrieve it again from memory. In other words, don't create a locally cached copy of this variable and just use that copy. Go actually get it every time you use it. Another way of putting this is volatile is a way to tell the compiler, do not optimize this variable at all. So you could do this for a number, there are a few reasons why one might do this. In our case, for a lot of these projects, we use volatile every time we have a variable that is being updated asynchronously. So these variables, as we'll see, they are updated in an interrupt service routine. And so we want for them to be volatile because if our threads, our main programming, are using those variables, and then they get interrupted by an interrupt service routine which modifies them, when we come back to our main program, our main application code, we want for it to use the most updated value. And so that's a way of telling the compiler, hey, this could change at any time. Please go get it every time you use it. Okay, so a couple of variables, another unsigned int here, a few more pound defines. We'll talk through these two. These will become clear when we look at the data sheet for the DAC. In short, this is a template for the data that we're going to be sending to the DAC. You'll see 4 configuration and control bits in the most significant bits there, 0011 in the case of DAC config A, 1011 in DAC config B. The lower 12 bits there are where we're going to put the data to send to the DAC. Yeah. It is not, it's a good question. uint16t is not a custom data type. It's a 16-bit unsigned int. On this system, we could have alternatively put their unsigned short DAC data, and it would mean the same thing. The uint16_t there makes our program, again, it's not of tremendous relevance for this class because we're all using the same hardware, but it makes it a little bit more platform independent. The word short, in our case, on our devices, means 16 bits. If you were to go to a 64-bit processor, short might mean 32 bits. But uint16_t means unsigned 16-bit integer on any platform. So you'll see uint16_t, uint32_t, uint8_t. Okay. And like I said, for us, we could alternatively use char, short, int, and they mean 8, 16, 32 bits. Okay, and then we pound define a few shorthands for some numbers. And the names of these macros sort of suggest how we're going to use them. We have one called pin miso, pin chip select, pin sclock, pin mosi. These are the GPIO numbers to which we are going to attach our SPI channel. And again, we can look at, if we look at the Pi Pico pinout, this will show us, let's see here. Oh gosh, it's not a good one. This shows us sort of our options. So we are using GPIOs 4, 5, 6, and 7 on SPI channel 0. So if you look at GPIO 4, you'll see that for GPIO 4, physical pin 6, SPIO 0 RX is a signal to which we can attach that GPIO. Chip select for GPIO 5, clock for GPIO 6 there, transmit for GPIO 7. That's where these numbers are coming from. See how they're used in a moment. A few more pound defines here. And then we declare a big array that we're going to call sign table. It's an array of volatile ints. And again, if you'll forgive me for waving my hands a little bit, we'll talk about how that's used in detail in a subsequent lecture. For now, suffice it to say, we're just making an array of 256 ints. The next place I'd like to go in this program, okay, there's a function here called alarm interrupt, sort of suggests what that is, but I'd like to pop down to main. As you all are aware, in any one of these programs, main is special. Your code starts executing at main. And just like in the Blinky example, the first thing that we do here is call a CSDK function called stdio init_all. Among other things, one of the things that this does is set up a UART channel on UART interface 0 so that when we print messages, if we hook up a USB to UART converter, we can see those messages on a serial terminal. And in this case, the message that we would see is hello DAC. The next couple of lines of code that we see are two CSDK function calls, each associated with the SPI peripheral. The first is called SPI init. It takes two arguments. The first argument, we pass in our macro SPI port, which you'll see we have associated with lowercase SPI 0. The CSDK uses that text string, SPI 0, as its indicator for SPI channel 0. There are two SPI channels. We could alternatively have SPI 1 there. We would just have to be careful that we're then using the GPIOs associated with SPI channel 1 instead of SPI channel 0. The second argument here is the clock rate for this SPI channel. We have it set to 20 million, which means we are going to do transactions at 20 million bits a second. How would we know what number to put there? Where would we look to figure out what number we should, to figure out how quickly we should be setting our SPI clock?
I would assume the datasheet for the specific SPI device you're interfacing.
Exactly, yes. So we would look in the datasheet not for the RP2040, but for the device that we want to talk to with the RP2040. And that datasheet will tell us the fastest rate at which we can communicate with it. And so we would look in that datasheet. We'll look at it in just a moment to figure out what number we should put there. In this case, we're communicating with our little DAC device. And when we open up the datasheet for that DAC device, what we'll see is it says, I can talk to devices as fast as 20 megahertz. So we put 20 million there. The next call here configures that SPI channel. And I want to go over to some slides for a moment to talk about how SPI works to substantiate some of these arguments. But let me just say, first of all, what they are. We call SPI set format. This configures the SPI channel. The first argument is the channel that we're configuring. The second argument is the data bits per transfer. For a single SPI transaction, are we going to be sending 8 bits or 16 bits or 32 bits? We set that configuration here. That too, we would learn what we should put there by looking at the data sheet for the device we're talking to. The next argument is the polarity. We'll look at this in just a moment, but this has to do with the clock, the phase, and the order. So let's talk a little bit about how SPI works so that we can understand what this means. So SPI stands for Serial Peripheral Interface. It is a protocol by which a single main device can communicate to a whole bunch of separate secondary devices. To set up an SPI connection among a bunch of devices, all of the devices with which the main device is communicating share 3 lines, 3 wires. They share a clock line, they share a MOSI line or an SDO line. That's information coming from the main device to the secondary devices. They all share MISO lines or SDI lines. This is for information traveling from the secondary devices back to the main devices. And then each one has its own separate chip select line. So if I'm the main device, if I'm the RP2040, and I want to talk to one of my peripheral devices, the way that I go about doing this is I drop the chip select line associated with that device. That's how I tell that device I'm about to talk to you. And the other devices will notice that their chip select lines are still high, and they'll say, oh, whatever data is about to appear on this data line, that's not intended for me, so I'm going to ignore it. So I drop chip select, and I start putting clock pulses on the clock line. And synchronously with each one of those clock pulses, I put 1 bit of data on the MOSI line, which goes to the device I'm communicating with. Simultaneously, with each clock pulse, the device I'm communicating with puts its own data on the MISO line or the SDI line, and I absorb the data from that device. So let me show you another picture of this. So the main device, in this case, is communicating to the secondary device. This is sort of a picture of an 8-bit data transfer, but like I said, you could have 16-bit transfers or 32-bit transfers. Read the data sheet for the device that you're communicating with. So what happens here is the main device, in our case the RP2040, has a shift register that lives internally to it. The device that we're communicating with has its own shift register that lives inside of it. When I want to communicate with this, I drop chip select and I start sending clock pulses. With each of those clock pulses, I shift 1 bit from my shift register, the least significant bit of my shift register, into the most significant bit of their shift register. And then I do it again and again and again and again and again. In this picture, I would do that 8 times. And after having done that 8 times, the contents of this shift register would now live here, and the contents of this shift register would now live here. And so the thing to notice about this as a protocol is it's full duplex, which is to say we can send information and receive information at the same time. And in fact, in the case of SPI, it is necessarily full duplex. In order to receive information from the device that I'm trying to talk to, I have to send it something. Now, depending what we're talking to, maybe you're just sending it junk, but you have to send it something in order to get something back. In the case of the DAC, as we saw in the code, we're doing 16-bit transfers, so you can imagine each of these shift registers is 16 bits long. And there will be 16 clock pulses associated with each of these transfers. Now, when we were looking at that line of code, there's a bunch of these configurations here, right? Data bits per transfer, the polarity, the phase, and the order. If you think about this for a moment, you'll notice that there are a couple of degrees of freedom here. And those configurations are setting those degrees of freedom. So 1 degree of freedom is my clock line idle low, active high, or idle high, active low? That is to say, when I am not doing a data transfer, is my clock line sitting at low voltage, and then when I start pulsing it, I pulse it high? Or alternatively, when I'm not doing a transfer, is my clock line sitting at high voltage, logical 1, and then I pulse it low? That is an adjustment of the clock polarity. The other degree of freedom here is, am I going to change the data on the data lines on rising edges of the clock or on falling edges of the clock? And so, the degrees of freedom here, right, there's 4 SPI. What we're looking at a picture of here is polarity 0, phase 0. Polarity 0 means that the clock line is idle low, active high. Phase 0 means that the data is stable on the rising edges of the clock and changing on the falling edges. So what that means is if I'm the RP2040 communicating with the DAC and I'm trying to, if I'm communicating with some extra device, I won't check the data on the data lines on the falling edges in this configuration because it's going to be transient, right? It's going to be changing. But I'll check it on the rising edges because it's stable on the rising edges. But there are some devices set up differently. This is an illustration of polarity 0, phase 1. Polarity 0 means the clock is still idle low, active high, but now our data is changing on the rising edges and stable on the falling edges. Or, of course, you could have your other 2 options. Polarity 1, clock phase 1, polarity 1, clock phase 0. This, too, in order to figure out what configuration you should set up in your code here, this comes from the data sheet for the device with which you're communicating. That's how you learn how you should set up this channel. I'll mention, too, I probably shouldn't even tell you this, but if you get this wrong for an SPI device, you're not actually going to damage anything. And so just trying all 4 is not going to hurt anything in this particular case. And it doesn't take that long to look, but you should look at the data sheet. And in fact, let's go look at the data sheet, just so I can show you what I'm talking about. So the device with the DAC that we're going to be using, the digital analog converter that we're going to be using in Lab 1 is the MCP4822. And let's see, if we scroll down here, the first information of relevance here is the pinout diagram. VDD is where you apply power, in your case 3.3 volts. Chip select is our chip select line. Here's your S clock line. Here's your SDI line. So that is information coming from the RP2042, the DAC. Notice that there is no SDO line here, no MISO line, because we don't care about any information coming. The DAC is a device we're just sending stuff to. We don't actually care to get anything back. Now, every time we do one of these transactions, something's appearing in our receive buffer. It's gonna be nonsense, right? We don't have it connected to anything. But there is no actual SDO line back to the RP2040 in this case. It's a 2-channel DAC, so you can have different voltages coming out of V out A and V out B. VSS here is their symbol for ground. LDAC, for our purposes, is not something that we're going to worry about. You'll just hold that low. That is if you were to hold the LDAC pin high, you could send a value to the output A channel and the output V channel, and then when you drop LDAC, they appear on the same outputs or the 2 outputs at the exact same time. So if you really cared about timing between the 2 outputs, you could control that with LDAC. You'll be setting this up on the breadboard in lab today or this week. But if we scroll down, I wanted to show you where you would learn some of this information about, the SPI channel. Let's see, there's a better picture down here, I think. Okay, let me pause here. You'll remember in the code, we had this DAC config channel A and DAC config channel B up here, and I said, these bits are configuration and control. These bits, we're going to put 12 bits of data to send to the DAC. Here's where that comes from. So we're using the MCP4822, the 12-bit DAC. What this is showing you is that for our 16-bit transaction, bit 15 is where we specify where we'd write, whether we would like for the voltage to appear on output channel A or output channel B. 1 means B, 0 means A. Bit 14 is a don't care, put a 1 there or a 0 there. The system doesn't care. Bit 13 is a gain selection bit. Basically, what range of voltages do we want to come out of this thing? Bit 12 is a shutdown control bit, turn the system off if we want. Bits 11 to 0 is where we put the actual data we're sending to the DAC. But if we scroll down a little bit further, this is what I wanted to show you. So here, for instance, are some timing diagrams. What this shows us is this particular device expects a 16-bit transaction, and furthermore, we can communicate with this device either in mode 0, 0, clock phase 0, or phase 0, polarity 0, or alternatively in mode 1, 1. And it can understand communication in either mode. We have our program set up to mode 0, 0. Okay, so all of this, these 2 lines, I'll get you in just a sec. These 2 lines are configuration of the SPI peripheral. We are setting up the speed of that channel, how many bits per second. We're setting up the data bits per transfer, the clock phase, the clock polarity. The order, by the way, is just most significant bit first or least significant bit first. And we've learned all of these configurations from the data sheet for the device we're communicating with, in our case, the DAC. Question?
On the data sheet, what was with the clock cycle 3 of SCLK? It's like longer than the other ones?
I don't know. I have to read this carefully. I can't tell you in real time. Oh, it could be as simple as that, just to fit that amount of text in there. Yeah, yeah. Other questions? Okay. So we're still down in main, right? We're setting up our SPI channel. We haven't actually done any SPI transactions yet. We're just setting it up. Then we set up our GPIOs. We're setting up one GPIO that we're calling ISR GPIO. And this is set up identically to the LED GPIO that we were looking at last time. We're just initializing it. Remember that says I'm going to use this GPIO from the processor. I'm going to control it from the ARM. We're setting its direction to an output because remember, they're automatically set into an input to protect you from yourself. And then we are setting it low for now. What we'll see in a moment when we look at this is every time we enter our interrupt service routine, we're going to set that GPIO high. And every time we leave it, we're going to set it low. so that we can probe that particular GPIO and put it on the scope and measure on the oscilloscope exactly how long we're spending in our interrupt service routine. You will be challenged to spend as little time there as possible. And then we set up our SPI GPIOs by calling a GPIO set function a number of different times. The first argument of this is the GPIO number that we would like to set. Remember that all of these are just GPIOs, 4, 5, 6, and 7, come from the pinout diagram. And then we're saying, please associate that GPIO with the SPI peripheral. Not the SIO, not an I2C channel. What we're saying is that GPIO is now connected to the SPI channel, and the SPI peripheral will be controlling it. We populate our sign table. Again, forgive me for waving my hands for today. We're going to talk about this in detail probably next time, but for now, suffice it to say, we go through and just add a bunch of ints to our array of ints, okay? All right, and then we set up our timer interrupt. And I want to pause here for a moment and talk about this timer. How best to do this? Let's go to the data sheet here. So let's see, if we go to the data sheet, we can scroll down to the chapter associated with timer. Oh, here it is. And I want to talk a little bit about this peripheral, because remember, and I keep drilling this point because it's an important one. Every one of these peripherals is its own separate piece of hardware. And the data sheet is where you read about that hardware. The SDK API guide is where you learn about how you configure and control that hardware. So given that we're now going to talk about a new peripheral, which is this timer, let's talk a little bit about the hardware, and then we'll talk about how we configure and control it. So the timer on this device, each of these RP2040s, contains within it a single microsecond, 64-bit microsecond timer. So that is to say there's a system on the RP2040 that is incrementing, it's counting at 1 megahertz. Once every microsecond, it increments by 1. It's 64 bits. Now, how does that work? All of our registers are 32 bits, but we have a 64-bit timer. Well, we put the least significant 32 bits in one register and the most significant 32 bits in another register, right? And at once per microsecond, we increment that. And when the lower 32 overflow, we get a 1 in the top one. Okay, here's the question. It's taking once per microsecond, 64 bits. How long do you have till it overflows? Let's see if we can figure this out. So once per microsecond, so that's 1, 2, 3, 4, 5, 6, 1/1,000,000th of a second, and then it will tick 2 to the 64th times. So that many seconds, oops. Okay, that many seconds, which means that many minutes, which means that many hours, which means that many days, which means almost 585,000 years. It's a pretty darn long time. And so if you're, yeah, it's pretty safe to assume that this is going to be increasing for the duration of, your project. Though I will mention, we're about to look at how we actually associate a timer interrupt with this peripheral. The timer interrupt can only see the lower 32 bits of this timer. So that will overflow every about 1.2 hours, like 72 minutes. Okay, so if you are trying to schedule execution of code in the future, in a distance of the future that exceeds about 70 minutes, there's another peripheral on this device that we'll talk about later, the real-time clock, and you should use that one instead of this one. Okay, so the 64-bit timer, you've got 500,000 years to spend. The 32-bit timer to which we can actually attach these interrupts, you've got about 70 minutes to spend. We are going to be asking for this to fire at 50 kilohertz, 50,000 times a second. Okay, but so we've got this 64-bit incrementing timer. Associated with this associated with this is a series of registers. The ones I want to draw your attention to, let's just look at all of them actually. Okay. So we have two registers associated with the actual time, the lower 32 of those 64 bits, the upper 32 of those 64 bits. And then we have four registers called alarm 0, alarm 1, alarm 2, and alarm 3. What we can do is we can write a 32-bit value to any one of these registers. Say we write a 32-bit value to alarm 0. And when there's a match between the lower 32 bits of the incrementing timer and the 32 bits in alarm 0, we can set it up such that an interrupt fires. So we can, if we care to, we could read the current value of the lower 32 bits of this timer. We could say, all right, I would like to schedule code to execute in 1 second. How many ticks of that timer is that? Figure out what that number is and write it to say alarm 0. And as long as we configure the interrupt associated with alarm 0, then when there's a match between the value in alarm 0 and that incrementing timer value, the interrupt fires. Now it fires once, and so if we want to repeatedly schedule execution of that code like we do in lab 1, then one of the things we have to do in the interrupt service routine is rewrite the alarm register to reschedule it again. This, by the way, if you have some experience with different microcontrollers or have worked with different sort of similar systems in the past, there is some variation in how this sort of timer hardware works in different devices. There are many devices that don't work exactly like this, but are instead set up as repeating timer structures. You say, please execute every X microseconds or something. This is different. We have to reschedule it every time. Now, there's some higher level CSDK functions that emulate that behavior, but we'll talk about that in a little bit. Okay. And then down here, we have some interrupt connected registers. This is, we'll look at this in code, but it is by way of, for instance, this INTE, interrupt enable register. This is how we tell the timer, please turn on interrupts for alarm 0 or alarm 1 or alarm 2 or alarm 3 or all of them. So we have to tell the peripheral to turn on interrupts. And then as we'll see in our program, we also have to tell the ARM processor, hey, please listen to interrupts from that peripheral. So we have to configure both. So we'll see both of those in there. Questions about this? Let me just see here before I leave this data sheet if there's anything else I want to mention here. This timer is not the only timer resource available on the RP2040. It is, I think, the simplest, and so it's a good one to start with. But each PWM channel also has its own associated counter that you could set up as a timer. You could set up the PIO processors as timers. Those, if you cared to, you could have those implemented full bus rate, 125 megahertz, or overclock at 250 megahertz. DMA channel has internal timers, and then the Cortexes, the ARM Cortex M0s also have timers as well. But this is the simplest one, and it's a good one to start with. Okay, so then with the few minutes we have remaining, let me just look at these, a couple pieces of code here. So line 113 here, remember we were just looking at the registers associated with that timer. In line 113, we're going to the INTE field of the timer hardware struct. That's the interrupt enable field for the timer. And we're saying, please turn on the interrupt associated with alarm num, which we've set to 0. So it's saying, please turn on the interrupt associated with arm 0. That's a command to the timer, telling the timer, please turn that on. The next line here is saying, please associate the following function with the alarm interrupt. We'll look at this function next time, but it's this one up here, right? We make a function, and we're saying, hey, every time that interrupt fires, I would like for you to call this function as the associated interrupt service routine. We turn on the interrupt, right? So that's telling the processor, hey, please listen to interrupts from the alarm, okay? And then this last line here is us actually setting that alarm register. So that schedules the first execution. Yeah.
Can you have multiple alarm interrupts configured, and in that case, do they all call the same function?
You can. So let's look at the. I'll show you this very quickly. So there's 4 alarms, And if we take a look at the, let me find it here, SIO interrupts. Okay. Sorry for the scrolling. Hold on. Let me find the link. Interrupts. Okay. I think I mentioned briefly in the first lecture that the two processors share 26 interrupts. Here's those 26 interrupts. What you'll see is there's 4 named timer underscore interrupt underscore 0, 1, 2, and 3. Those are associated with alarms 0, 1, 2, and 3. And so you can have each one will throw a separate interrupt, and you can have a separate interrupt service routine associated with each of those. We're about out of time, so I'll continue this story next time. I will be in lab this afternoon to talk to the Monday folks, and I'll see the rest of you Wednesday, if not before.